All right, welcome and thanks for joining for section 2.2. As you can see, what we're talking about here is polynomial functions of higher degrees. So in 2.1, we sort of zeroed in on quadratic functions. Now we're going to talk a little bit about what can we say about functions that aren't to the second power. So graphs of polynomials, just in general, what that means is that they have to be continuous and smooth. So meaning, when we talk about continuity, there are no jumps, which okay, whatever. This is a J, jumps, or domain restrictions, and there are no rigid curves or rigid turns or sharp turns. And that's the idea of smooth. So continuous, meaning there's no jumps. I could draw this graph without picking up my pen, and there's no restrictions, and there are no rigid turns. So looking at these, letter A, this represents a polynomial function because it has smooth, rounded curves. Part B, this does not represent a polynomial function. While it is continuous, I could draw this without picking up my pen, it comes to a rigid turn where I'm taking like that jagged edge. Here, part A, we have a continuous graph. You know, I could draw this without picking up my pen. It just goes smoothly throughout there. Part B, that we have some jumps. So here we're looking at something piecewise, where I could pick up, or I could keep my pen down. I get to this point and I'd have to pick up my pen, go over here, draw that open circle, and now it's become discontinuous. So that's just sort of, what polynomial functions are, or graphically what they look like. Some basic polynomials of higher degree, so 3, 4, 5. Here we have an x cubed graph. Remember, this is one of the ones that you definitely have to be familiar with, but x cubed, you can see that it has that sort of noodle shape. If we look at the x to the 5th, we have that same sort of like noodle S shape, but we'll talk about different things that can happen when it's to the 5th as opposed to the 3rd. Notice too, x to the 4th and x to the 6th, they have that same basic parabolic or parabola looking shape. Shifting of these polynomials is the same. So if we talk about a horizontal or a vertical shift, throwing all the way back to section 1.4, those properties work the same way with polynomials of higher degrees. So a shift up 3 means there's plus 3 at the end. All right, moving along. A cubic polynomial. So when we talk about a cubic polynomial, we're talking about something in the form of f of x equals a sub 3 x cubed plus a sub 2 x squared plus ax, or if you wanted a sub 1, x to the first, plus a sub 0, and then there's no x. Notice that any of these coefficients can be any real number, including 0, except the first one. So that first coefficient, a sub 3, that cannot be 0, because if it were, this wouldn't be a cubic polynomial. You would be saying that you don't have this term, so it would become quadratic. So the leading coefficient, which we call a sub n, is the coefficient of the highest powered term. So the coefficient of the highest power term. And that's just important to keep in mind. A lot of times I'll refer and say like, okay, so the leading coefficient is, it doesn't necessarily mean the one that comes first. It means the one that's attached to whatever is the highest powered term, regardless of where that shows up in the polynomial. The leading coefficient and the degree of the leading term can help describe what's called the end behavior of a polynomial function. So the leading coefficient, when we look at that leading coefficient, what we're concerned with is whether or not it's positive or negative. We don't care the actual value if we're talking about end behavior. We just care about, is that leading term positive or negative? And then the degree, what we're concerned with the degree is whether or not it's even or odd. So I'm going to throw back a slide now. Looking at this, notice even things, they have the same sort of end behavior. End behavior meaning as I move all the way to the right, what happens? As I move all the way to the left, what happens? Okay, well, this is increasing either way. Increasing, increasing, or rising. Maybe you don't like increasing because this is a decreasing line. So it rises on both sides. Something that has an odd power, it's rising on the right, but falling on the left. Rising on the right, falling on the left. So we can avoid using that increasing, decreasing lingo. All right, slide 4. This is going to be a little bit visually overwhelming. It's really good notation, though. So if n, the degree, is odd. So I'm talking about something like x cubed, x to the 5th, x to the 7th. A sub n, the leading coefficient, being greater than 0, so the leading term is positive, means that the right side rises and the left side falls. Notationally, this can also be written as x goes to infinity. So as I'm going towards positive infinity along the x-axis, meaning the right side, f of x, meaning the y value, is rising, so it goes to infinity. And as x goes to negative infinity, f of x goes to negative infinity. So when I read this as x goes to negative infinity, I'm thinking as this function moves to the left infinitely, the y value is going towards negative infinity. So as I'm moving infinitely to the left, I'm going infinitely downward. If, however, the degree is odd and the lead coefficient is negative, that means that the right side falls and the left side rises. This is essentially just a reflection. You know, again, going back to section 1.4, we've reflected this. Notationally, this can be written as x goes to infinity. So as I'm going to the right, I'm falling. So f of x goes to negative infinity. And as x goes to negative infinity, so as I go infinitely to the left, I'm rising, so f of x goes to infinity. Now, we also have what if the degree is even? So now we're thinking about something that looks sort of like a parabola. A sub n, that leading term, or leading coefficient, being positive, means that both sides will rise. You think about your just regular x squared. That's a positive leading coefficient. Both sides rise. So as x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, f of x goes to infinity. So here we're saying both sides rise. Both sides go to positive infinity. If the leading coefficient is negative, however, that means that both sides will fall. So as x goes to negative infinity, f of x goes to negative infinity. And as x goes to infinity, f of x goes to negative infinity. I sort of switched these ones, but the order of these don't matter. It's just saying that both of these things happen. But here again, when I'm reading this, as x goes to negative infinity, that's saying as I move towards negative infinity on the x-axis, the function is going towards negative infinity. So it's getting infinitely lower. All right, the next thing we talk about then is real zeros of polynomials. And you guys have talked about these before, you just haven't called them real zeros necessarily. These are really just x-intercepts. So if we said x equals a is a zero of the function f, or x equals a is a solution of the polynomial equation f of x equals 0, or x minus a is a root, I'm sorry, not a root, I'm just kidding, get rid of that, is a factor of the polynomial f of x, so x minus a is a factored form of it, or a comma 0 is an x-intercept of the graph f. So those are all saying the same thing. X equals a is a 0. X minus a is a factor. X equals a is a solution for when the function is equal to 0. And a comma 0 is an x-intercept on the graph. For any polynomial of degree n, the polynomial will have at most n real zeros. So if I have a polynomial with degree 5, there are at most 5 real zeros. There cannot be more than that. There can be less, but there cannot be more. Relative minimum and maximums also depend on the degree. For any polynomial of degree n, the polynomial will have at most n minus 1 relative max or mins. I'll say mins or max. So again, if I'm thinking about that x to the 5th, that means that within the graph, or within that function, there is a total 4, because I subtract 1, possible mins or maxes. All right, we're going to skip over these examples and talk about the multiplicity of zeros. So if x equals a is a 0, and x minus a to the power of k is a factor of our polynomial, then a has a multiplicity of k. So, for example, if I have x minus 1 cubed, that is called a triple zero. Triple at x equaling 1. Because again, this is x minus a. So the minus is part of sort of that factor. A is just 1. Or you're thinking about what would zero out this term, positive 1. It's a triple zero because of the degree. That degree will help us when we're sketching. And we have a single zero, or just a 0, but for the sake of multiplicity, we'll say single zero at x equaling negative 2. If we wanted to graph this, let's just make ourselves a little graph. Oh, wow, that was really crooked. Let's make ourselves a better little graph. Oh, there we go. So here, we know that we have a 0 at 1 and a 0 at negative 2. Looking at the overall degree of this function, the overall degree is 3 plus another 1, so the degree is 4. Then I look at that leading term. The leading term is positive. So I know that this is something of degree 4. That's positive, so it has that basic parabola-looking shape. What we'll talk about sort of in the next slide, but what we'll talk about with these degrees is how you know sort of how the rest of this graph looks. But in this case, you'll just have to trust me. It looks like this ish. There could be some stuff happening inside here. We don't know that yet. All right, just talking then about what different multiplicity of zeros look like. So something with a multiplicity of 1 is going to look linear. Something with a multiplicity of 2 will look quadratic. Something with a multiplicity of 3 will look cubic. In general, what you want to keep in mind is that an odd multiplicity is going to pass through the x-axis. Something with an even multiplicity is going to touch but not pass through the x-axis. So for instance, if I want to look at x plus 2 cubed times x minus 3 squared, again, I'll draw a little function, or I'm sorry, graph. Here, x is equal to -2. Here, x is equal to 3 if we're talking about zeroing out those equations. The overall degree of this function, if I were to multiply this all out, I would get something to the 5th power. And if I'm talking about the lead coefficient, because this would be x and x, I know that it's positive. Something of degree 5 that's positive has that basic cubic shape. Which, I'm terrible at drawing cubic shaped things, but that'll work. So we go to -2. And we go to 3. So at -2, we have something that's starting down here. And then because this is a triple zero, odd multiplicities pass through the x-axis. So this is going to go through the x-axis. And then, I don't know, something up here happens. We don't know that. But then we look at this multiplicity. This is an even multiplicity, which means when we come back down to this point, we are not going to go through the x-axis. We are simply going to touch the x-axis, touch that little point right there, and then come back up. So there we go. We've got something to the degree of 5. And I'm just going to sort of get rid of that little hook that's going on there. That falls to the left, rises to the right. And there could be some number of other mins or maxes that happen here. Because this is degree 5, I could have 4 relative min or max. And looking at mine, I just have 2. So there could be some more going in there, but they're not crossing that x-axis anywhere else. All right, so I think that's all I have to say. It is. So make sure you go watch those example videos. They're mixed in a little bit there, but it's some really good stuff with just sketching, and hopefully it won't take too long. We'll always see.